Okay, so for this video, I want to look at Chapter 4.2, that example packet number 11b, which is a graphing of a cosecant problem. It's a transformation one. Um, and so, here, let's look at it. So it's going to be this one. So we know our parent function is going to be y equals cosecant x, and we know that that's got to turn into this new function, 3 cosecant 2x plus pi over 2 minus 1. And so the general point for the first function, for the parent function, is a cosecant of a. And then that's going to turn into some new general point. And the trick for it, remember, is take that ugly x term and call it a. And then if I solve for a, I get a minus pi over 2 equals 2x. And so if I multiply by a half, I'll get the x by itself. And then in order to figure out the phase shift, right here, phase shift, what we need is to do the horizontal stretching stuff first, and that becomes easier if we actually distribute everything here. So that becomes pi over 4 equals x. So then my new x value in this new function is 1/2 a minus pi over 4. And my new y value becomes 3 cosecant a minus 1. And so now I can figure out what my stretches and shrinks are. So in terms of horizontal, I'm doing a horizontal shrink by 1/2. And I'm doing a horizontal shift by pi over 4 to the left. And I'm doing a vertical stretch by 3, and then a vertical shift 1 unit down. And then there are these things here. Remember, vertical stretch and amplitude for sine and cosine problem. Well, actually, since it's not a sine or cosine problem, it's just vertical stretch. If it was sine or cosine, then you could call it amplitude. Period. Period is related to horizontal shrink and stretch. So the original period, well, actually, you know what? I'll do this at the end. I'll do the period at the end. Vertical shift, we already have 1 unit down. Phase shift is the pi over 4 to the left. And the reason we can say this is the phase shift is because phase shift, let's say, because already did the horizontal stretching first, horizontal shrinking in this case first. If we had done the shifting first and said, like if we use this x value and said first shift it to the left pi over 2 and then shrink, do a horizontal shrink by a half, the pi over 2 would not be our phase shift because I did that before the shrinking. So you'd have to convert it to this so that you could do the shrink of a half first and then shift it by pi over 4. And you can call that your phase shift. So that's key. Horizontal stretching and shrinking have to come first. So here's kind of our blueprint for the transformations. Actually, this is the main blueprint. This is going to tell us what to do to our important features of the original cosecant graph. So the cosecant graph, to be honest, I never remember which one's cosecant and which one is secant. Instead, I just think, well, cosecant's like 1 over sine. And so if I do a quick sketch of sine right here, then I can figure out what cosecant looks like. And if you remember, you get asymptotes where sine has zeros. And then the peak and valley stay put because it's 1 over 1 and 1 over negative 1. And then if you remember, we get these kind of U shapes right here. And the period that we said we would take for cosecant was this one right here, from 0 to 2 pi. So I've got a few different things to keep track of here. I've got a vertical asymptote at x equals 0, at x equals pi, and at x equals 2 pi. And then I've got these 2 points right here. This one is at pi over 2 comma 1, and this one is at 3 pi over 2 comma negative 1. So those are the 5 things that I need to transform, and I am going to lay them out in order. So vertical asymptote x equals 0, followed by pi over 2, comma 1, followed by pi, x equals pi, sorry, vertical asymptote, x equals pi. And then 3 pi over 2, comma negative 1, and then x equals 2 pi is my last vertical asymptote. And the reason I did this is because all the x terms are now evenly spaced, and so then I know whatever they transform into are also going to be evenly spaced. So if I get the first two right, I can just figure out the rest by looking at the first two and how far apart they are. So the first vertical asymptote, if I use this blueprint, that's like saying a equals 0, so that's going to turn into 1/2 times 0 minus pi over 4, so my new asymptote's at negative pi over 4. And then if I plug in pi over 2 for a, right here, then I'm going to get pi over 4 minus pi over 4, so that's going to be x equals 0. Oh, whoops, so 0, comma something, and 1 is the cosecant a here. So if I plug in 1 down here, then I'm going to get 3 times 1 minus 1, so that's 2. And if you look here, well, this and this are pi over 4 apart, and I increase by pi over 4. So the next one's going to be add another pi over 4 to the previous x value, and then the next one's going to be add another pi over 4, and then the next one's going to be add another pi over 4. So, whoop, yeah, so that's going to be, let's see, that's 2 pi over 4, so this will be 3 pi over 4. And, oh, yeah, this is an asymptote, so it's just VA equal, x equals 3 pi over 4. And this is also a vertical asymptote on the new one. So really, I just need one more y value. That was y equals negative 1, so cosecant a is negative 1. If I plug in negative 1 here, I get negative 3 minus 1, so negative 4. And now I have enough to graph the whole thing. So my new graph is going to use these 5 features here. So let's see. I will go by pi over 4 on my chart, on my x-axis. So negative pi over 4, 0, pi over 4, 2 pi over 4, which is pi over 2, and then 3 pi over 4. Oops, sorry, that's my alarm. Okay, I don't know if you could hear that or not. And then I gotta go, let's see, up 2 units and as low as 4 units down. And I'll plot these 2 points here, so that's 0, 2 right there. And I've got pi over 2, negative 4 right here. I've got an asymptote here, an asymptote here, an asymptote here. And then I've got this going downwards and this going upwards. And let's see, what else do I need? That's really it. So there's my function right there. If you had to keep going, well, remember they alternate, so it's going to look something like this. If I ask for stuff like domain and range, well, the domain here, you can tell that, okay, I can't have pi over 4, and then it repeats every 1 pi over 4, 2 pi over 4. So it repeats this distance right here is pi over 2. So it repeats every pi over 2 units, so times k. So k is an integer. And then the range of the thing, notice you can be higher up than 2, including 2, and you can be negative 4 and lower. So it's going to be negative infinity up to negative 4, union 2 up to infinity. That's only if I asked for this, which I would probably end up doing on a test anyway. Okay, so I hope that helps a little bit, and a lot of other problems that involve secant and cosecant work just like this.